Thank you, Clemente, for the opportunity to present here today. Unfortunately, I don't speak any Spanish, so I have to take this presentation in English. But if you have any questions about the presentation or about the research, then please let me know, and I'm happy to answer them. So what I'll talk about today is about climate change and natural disasters. And I'm actually from the Netherlands. So in the Netherlands, our country is actually low-lying. So most of our country mass is located below sea level and below river level. And climate change adaptation is a very important issue there, of course. Because if you would not have coastal protection, like for example the dikes or storm surge barriers that are shown on this slide, then our country would be flooded continuously. So actually recently we've also been asked to conduct a study about flood risk adaptation in New York City, and we have actually been asked to do there a cost-benefit analysis of different flood risk adaptation strategies, and that's actually what I'm going to present with you today. So on the next slide I have an agenda, the outline of the talk. So I'll start with discussing the broader context about natural disasters and climate change, because this sounds very abstract always, but I think it's actually very concrete. So many of us have already seen large disasters on television which are somehow related to climate change or could be exacerbated by it. Then I'm going to discuss in more detail the study that we did for the economic cost-benefit analysis of flood risk adaptation measures in New York City. And I'm going to do that in several steps. But first of all, outlining the different flood risk management strategies that can be taken to protect such a city from flooding. Then I'm going to continue to discuss the overall methodology that we take, the different models that we use to do a risk analysis to estimate the impacts of climate change on flood risk, and to estimate the cost and the benefit of different flood risk adaptation measures. I'm going to then discuss the different model components in some more details, by discussing the cost of the flood risk adaptation measures and how we have derived those, and to discuss the flood risk modeling methodology that basically delivers the benefits of installing these adaptation measures. And in the end, we're going to discuss the results of the cost-benefit analysis and give some more general conclusions. To the next slide, please. So as all of you have seen also on television, is that New York has actually been hit quite severely last year by Hurricane Sandy. And this was actually a quite extreme impact on the city itself and on the US. So Hurricane Sandy was a very exceptional storm. It has a very large wind field. So it's a less than a 1 in 1 year event, so quite unlikely to happen. And because it was such a large storm with a large wind field, it pushed up a lot of water at the US shore. And by doing so, many areas were flooded, and in the US about $15 billion of damage has been caused. And especially exceptional was actually the impact on New York City, because quite often if a hurricane approaches the US coast, east coast, then the hurricane would go away from the city. Although in the past there have been storms hitting the city also, this hurricane actually continued on its track and really hit the city very hard. So in the end, about 70% of the city's land was flooded. More than 89,000 buildings were located in the flood zone, and massive damage was caused of about $19 billion. Next slide, please. Also in Mexico, a very severe flooding event happened, as you all know, in September. With the exceptional events that two hurricanes from different coasts were hitting Mexico at the same time. And so for example, Hurricane Manuel, which hit the southwestern Pacific, started out first, and then Hurricane Irene actually hit the opposite coast, and that caused large flooding, heavy rain, mudslides, and also a lot of economic damage. So about 20 Mexican states were affected. Large-scale evacuations happened, there were a lot of casualties, and the economic losses, so the damage was also very large. Next slide. So I think these type of events, they are not a standalone event, right? So they can be placed in a broader context of increasing natural disaster losses that have been occurring around the world. So as you see on this slide, this is actually the natural damages that caused have been caused around the world between 1980 until 2012. And in the green bars you see the overall losses, and in the blue bars you see the insured losses. It's very clear that these losses have been increasing. Right? So the immediate questions you may ask yourself, like, is this climate change? What's happening here? Are these losses increasing because we see more severe extreme weather events, or are other factors causing this trend? And there have been quite some studies that have been going on to try to explain what's causing these worldwide increases in natural disaster losses. And most of these studies have actually shown that it's mostly because of economic growth. So it's because more people, more economic values are located in hazard-prone areas, such as coastal zones. Basically, the losses of the natural disasters have been increasing already. But it could also be that climate change already has had an influence on these losses. But it's very difficult to prove in general, because these data sets, they don't go back very far in time. So it's actually difficult to really prove that this is really climate change. But it's probably a combination of both more people, more economic values in hazard-prone areas, as well as more extreme disasters that can explain a trend like this. So the next slide, please. So in 2012, actually, a special report has been published by the IPCC that basically tried to answer this question. So, have natural disaster losses around the world already been increasing because of climate change or not? And what confidence do we have in this? And how is this related to predictions in the hazards, so the natural science causing more of these events happening? And the evidence is kind of mixed. I try to summarize that on the slide here. So for example, if you look at the length and the number of dry spells, there's some medium confidence that this has already increased in the past. It is quite likely that in the future, because of climate change, such dry spells could occur more often. And the same about droughts. The droughts are very local phenomenon, so there's only medium confidence that these type of risks will decrease in the future. Then there are several predictions that have been made related to hazards that are related to flooding, such as heavy precipitation events. So it's quite likely that around the world these type of events have been occurring more often already, and that this will be more problematic in the future. The same with the intensity of tropical cyclones. From the past data, it's difficult to determine whether climate change has been increasing these events or not, because of problems in the database measurements. It is quite likely that in a warmer climate, these type of events will become more severe in the future. The same also with extreme coastal waters. So what has been observed already is that while climate change has been causing sea level rise, so the water levels have been increasing already. It's also had the effect that the extreme water levels have been occurring more often, and it's very likely that this will continue in the future. So if you especially think about the last three types of events, like floods, tropical cyclones, and higher coastal water, I think we should be very worried, right? Because the type of disasters that we have seen, the hurricanes in Mexico and the hurricanes in New York, although they cannot be directly linked to climate change right now, it's quite likely that in the future there will be more of these type of events happening, and we have to think about what type of measures can be put in place so that if it happens, that the impact in terms of casualties and in terms of economic losses will be less severe. Next slide, please. So some predictions have been made to try to translate these climate change predictions into risk increases. So if you, for example, have more severe hurricanes happening, what would this imply for the economic cost of these type of events? Here I show some results of this. So for example, empirical analysis conducted by William Nordhaus and also by my colleague Laurens Bauer and myself have shown that if the wind speed of hurricanes would increase because of climate change scenarios that are predicting that it would increase, for example, by a doubling in 2050, which would actually result in a doubling of hurricane damages already. So this is just the effect of stronger wind. Then there have been some studies conducted that also try to estimate, well, what's the effect of sea level rise on this type of damages. For example, a recent study has been published by Halligate and others in Nature Climate Change, have shown for coastal cities around the world, sea level rise by itself could already increase damages up to tenfold in the future because of climate change. So these type of predictions are quite worrisome. But of course this is very broad, these are very general predictions, while climate change has very local impacts. So the changes that are predicted to happen in climate will differ from one region to another region, and also regions have different vulnerabilities to these type of events. For example, a city like New York with very high exposed assets is in that sense maybe very vulnerable to coastal flooding and increased sea level rise, while for other regions where there is less exposure, it's maybe less of a problem. Right? So in the end, if you want to have a good adaptation policy, you first need to analyze the local risk, think about the local situation, what will be the climate change impacts there, and what can you do about this. Next slide, please. So what was the goal of the study? So we've been working on New York City flood risk management already over the last 4 years. But basically after Hurricane Irene occurred in 2011, the city became very interested in assessing adaptation strategies. So they basically asked us to perform a benefit-cost analysis of different adaptation measures that they were considered to be undertaken. And the key questions were, should New York City, for example, invest in flood-proofing their buildings, so have stricter building regulations so that the damage will be less if a flood would occur, or should the city invest in large-scale engineering measures, so for example install coastal protection or install storm surge barriers in order to prevent the floodwaters from entering the city. And the current flood risk management policy was very focused on building codes, so try to elevate buildings, for example, so that damage during floods will be less. But the general expectation was that maybe in the future that's not feasible anymore. So maybe they would need better coastal protection in order to protect the city from sea level rise. But of course the question then is, are these investments worthwhile? Because it basically costs a lot of money to build such a system, and does this pay off in the terms of the reduced risk that this delivers? And also a key question is, how does this depend on climate change? Right? So maybe investing in large-scale coastal protection is not worthwhile now, but maybe in the future, if risk increase, then maybe it is a good investment, right? So that was also a key question to be addressed by this type of research. And well, because we answered this question using many different models or methodologies, we thought it's also very important to look at, well, what are the model assumptions that are driving our results, and are our recommendations that we give to the city in the end robust to the type of assumptions that we are making in this research. So that's also what I will address during this presentation. So the next slide, please. So what are the different type of flood risk management strategies that we are considering? So in terms of building codes, they were thinking about flood-proofing new buildings that are already located in the flood zone, or you could think about adapting only buildings that are newly built, because then if they are newly built, it's probably easier to build them in a flood-proof way. Another question is, to what level should the building be flood-proofed? So to what height? So if you want to elevate, for example, a building, should you do this for 2 feet, or 4 feet, or for 6 feet? So we also try to answer that question in our cost-benefit analysis. Then the question was also, to what types of area in the city should this be applied? Should this be applied to the areas that are affected by a flood that occurs 1 in 100 years currently? Or should we also apply these type of measures in areas that can be flooded 1 in 500 years? So that was also part of this research. And then the other strategy, S2, was basically consisting of different storm surge barriers that can close off the city during a flood, and coastal protection around these storm surge barriers. So now I'll discuss these strategies in some more detail. Next slide, please. So here I give you an example of the 3 building code measures that could be taken to reduce the flood risk in the city. So the first measure is to elevate a building above the flood level. And I show here a picture of an elevated house. So this basically would mean for an existing building that you would lift up the whole house, build a new foundation underneath it, and so that if a flood happens and the water comes in the city, that building will not be damaged. You can also do this when you build a new house. You just put some more dirt underneath it, and then you build it higher. Another strategy is to wet flood-proof a building. I show that here in the middle of the slide. So with wet flood-proofing a building, it's not elevated, but basically you use different types of building materials to make sure that the damage during a flood will be less. So the water, as you see, can still enter the lower part of the building, but if you would install all the electricity a little bit higher, and if you would coat the walls of the building, then the damage would be minimized. Another strategy is to dry flood-proof a building. So an example of that in this picture. If you dry flood-proof a building, you basically try to keep the water out of the building. So what you can do is you can install sandbags or flood shields around the house, and you can coat the walls outside the house in such a way that if the water is standing next to the house, it's not entering it. You see in the graph, the picture here. So in that way, the building will not have any damage. The next slide, please. Then there are basically two types of different storm surge barriers that are being considered to be installed by the city. So the first storm surge barrier strategy is actually called environmental dynamics. And what it basically consists of, here you see a graph of New York. So here you have Manhattan, Queens, Brooklyn, Staten Island, and the Bronx. And the idea is then to install 3 storm surge barriers, one here, one here, and one here. So these are located at the Arthur Kill, the Verrazano Narrows, and the East River. And these barriers basically consist of gates that can be closed if a storm happens. And then if a storm happens, it means that the water cannot enter the Hudson River or the East River anymore, so there will be no flooding. It's actually called environmental dynamics because these barriers are constructed in such a way that if there is no flood, they're basically open. So as you see an example of the barrier here, you see normally the water can just flow through the barrier, and here there are all sluices that are also open. So in that way, the environmental values are not disturbed. So this is better for the water quality because it's not completely blocked off. But also if you install these type of barriers, you need additional coastal protection. And that's what I show here in these yellow parts. You basically need to elevate all these coastal protection at the coast. And the reason is if there's a storm coming and you would close off the water with a barrier, the water will be pushed outside the barrier system and could flow over the land around it. So if you install these barriers, you also need to have dikes and coastal protection around it. The next slide, please. And there was also another strategy that is being considered to be installed, which would actually consist of one large barrier here that could close off the whole harbor of New York and the bay. And so in that, if you would install the barrier here, the advantage would be that you need a lot less other coastal protection. Right? So the other areas here that need to be protected are much smaller than at the previous barrier strategy I showed on the previous slide. So this would be a cheaper option. And you also need to install a small barrier here to protect this low-lying airport. So this measure can be less costly because you need less additional coastal protection. But the disadvantage of this very large barrier here is that it would block a lot of the water, so that the water quality in the bay could deteriorate. Next slide, please. The city will be flooded, and also how high will be the water level at different locations. So for that you of course need information about the elevation of the land in the area. Now if you know what areas will be flooded, there's basically a flood damage model that will calculate what will be the damage. So you can do this if you know what buildings are located in the flooded areas and what their value is. And then according to the water level for each storm, you can calculate for every building how much the damage will be. And if you add that all up, you will know the damage that will be done to the city. And then the output would be the loss for a storm. But if you do this for many storms, you can also calculate the average loss per year. So you have to do that first for the baseline, and then we do that, the same thing, but then we impose certain measures. So for example, you have building codes, or you have a flood risk management strategy with the barriers, and then you calculate what the damage will be in that case, and then the difference between that and the loss without any measures will be the benefit. which will enter the benefit cost analysis. And of course, you also need the cost of the different strategies, which is generally based on engineering estimates of how much it will cost to implement an adaptation measure. Next slide, please. So now we'll discuss the cost of the different measures in some more detail. Next slide. Yeah, next one, please. So first of all, starting with the building code measures, we actually looked at the literature of engineers who have estimated how much it will cost to flood-proof these different types of buildings. So how much does it cost to elevate them, to dry flood-proof them, or to wet flood-proof them. And this will depend on what material the building is made of. Then what we did, for every building located in the New York City flood zone, we have information about its characteristics. So what type of walls the building is made, etc. So then for every building category in the city, we can estimate how much it costs to flood-proof that particular building. And then if you aggregate that all up, then you know the cost of implementing a building code strategy in a certain area. So here I show you some cost estimates that come out of that approach. So first of all, the elevation of buildings. You can do this for 2 feet or 4 feet or 6 feet. For existing buildings, it will be very expensive because you need to lift up the whole building, build a new foundation underneath it, which is an expensive method. So it would cost between 2 billion and 3 billion US dollars to do that for these buildings that are located in the flood zone. That's very high. Now, if you would apply that to all the buildings that are expected to be newly built until the year 2040, it will be a lot less. So it would only cost 80 million up to 240 million, depending on the height that you would elevate these houses. And the reason why this is much lower is because it's much cheaper to elevate the house when you're constructing it. The wet flood proofing of the buildings is less costly to do than the elevation for the existing buildings, so it costs between 250 million and about 1 billion. And it's also between 70 and 260 billion for new buildings. So that doesn't matter that much compared to the elevation of new buildings. And the cost of dry flood proofing are a little bit higher if you do this for 2 feet only, but about the same if you do this for 6 feet. And the reason is that the startup cost of dry flood proofing a house are high because they need to buy flood shields, etc. So it doesn't cost that much more to do this for additional height. And for new buildings, that would be between 170 million and 260 million. So it's more or less the same as the wet flood proofing, except for the 2 feet level in which you apply this. Next slide, please. So now the cost for the flood protection and storm surge barriers. We estimated those on the base of engineering companies that made designs of these barriers and estimated their cost. So there are different engineering firms involved who have provided the cost of installing these 2 storm surge barriers options. But of course, we were not really sure whether these engineering firms were correct or honest in the way they would report their costs. Because maybe they would underestimate them in order to get the job and build them. And so what we also did is a comparative study of other surge barriers. So we looked at all storm surge barriers that have been built around the world, looked at the characteristics of these barriers, how much they would cost, in order to assess whether the engineering cost estimates were more or less the same as the cost estimates of barriers that have been built in other places, like the Netherlands or New Orleans. And they actually found out that that was the case, so that the engineering firm estimates are reasonably reliable. Then we also estimated the cost of the local flood protection to look at how many local flood protection measures like dikes have to be installed around the coast, because these need to be included in the investment cost of the strategy. And then we see the investment cost here. So for the environmental dynamics, so consisting of the multiple barriers that are open if there is no flood, the total cost would be 21 billion US dollars to install that strategy as well as all the coastal protection. So that's very expensive. And the maintenance costs are about $100 million per year. And you have to imagine that this structure will stay there for about 100 years. So every year they have to pay them, they will do this for 100 million per year. So it's a very large component of the cost. But the outer harbor barrier is actually a lot cheaper because you have to install only one large barrier and the additional cost of protection is less. So you could install that one for about 13 billion US dollars. But the maintenance costs are also quite high, even a little bit higher, because it's expensive to maintain one very large barrier. The next slide, please. So now we know the cost of the different measures. In order to do the cost-benefit analysis, we need to estimate the benefits, right? So if you install it, how much money will you basically save? So this is estimated using the chain of models that is shown on the graph here. So first of all, we have 549 hurricane simulations of New York City that were provided to us by MIT and Princeton. And for every hurricane simulation, we know the water line, so how high will be the water at the shore. What we also know is the height of the land. So we have a digital elevation model, so it shows for everywhere in the city how high is the land located. If you combine these two pieces of information in the inundation model, we can calculate for every storm what area of the city will be flooded. So you basically create an inundation map, which shows you what is flooded and how high is the water level. We also know, the city gave us the information for every building in New York, what type of building is this and what is its value. So if we combine that with the inundation map, we have a mathematical model that calculates for every building what will be the damage. And it basically depends on the water level. So if the water level is low, the damage is less. If the water level is high, the damage for the building will be more. And these are all based on empirical relations that have been observed during previous floods. So then for every building we can calculate the damage, and then we can aggregate that up, and then we have the damage for the city. And we know that for all the different storms, and we can calculate the average risk. So what will be the average flood risk in a year? And it's basically summarized here in this picture, where the red indicates high risk, and the less red indicates less risk, and the white indicates no risk. And then you see that some places like Long Island, Brooklyn, Queens, and Staten Island, they have a quite high risk because they will be flooded quite often. But other places like Manhattan and the Bronx is less because it's a little bit more highlighted. Next slide, please. So this is another way to represent the risk estimate. So this basically shows the damage for different storms with different probabilities. So for example, the highest damage to buildings would be in the order of about 27 billion. It's very unlikely that this will happen, so that's a very severe storm. While we also know that there will be smaller storms that can happen with a higher probability, but they will cause less damage. And now if you have this curve, so we have this estimated for all of the different storms that can happen, you can calculate the average risk per year. Next slide, please. It could increase by 480% in 2015 and 1200% in 2018. That's a very large potential increase in risk because of both sea level rise and increased strength of the hurricanes. There's even more extreme scenario, which is a high rapid ice melt. It was 100 centimeters sea level rise in 2018, and that would increase risk by 2,300%. So that's a huge risk increase, which we consider well, the worst case scenario that's possible. Next slide, please. But we also know that it's not only climate change that's influencing risk, it's also how many more people are located in the city. So here I show a graph of the cumulative value of the build-up areas in the flood zones in New York from 1880 to 2000. And you see that this has increased substantially, right? Just because there are more and more people who are living there. But we also have projections for the future. So the city gave us projections about how much more people they expect until 2030. We translated that in how many more buildings will be located in the flood zone and calculated the risk increase because of that. And the risk increase will be about 15% in 2040. So it's a lot less than what climate change can do with the risk, but it's still important to include that in the analysis. And we assume here that population will be constant after 2040, which may be unrealistic, but we basically have no idea what will happen with the population after that period. Next slide, please. So the next step is then to calculate with the model the risk reduction of the different strategies. So here I show the results for the building code strategies. So the elevation of existing buildings, you can only reduce risk with that between 20 and 30% because many existing buildings cannot be elevated. While for new buildings, it could reduce their risk to 65 to 95%. So that could be quite an effective strategy to limit this. While with the wet floor proofing and dry floor proofing, usually reduce risk somewhere between 10 to 25% to existing buildings, a bit more with dry floor proofing, while between 20 and 40% of the risk can be increased to new buildings. And the reason is that it's not a 100% risk reduction is because if you wet floor proof a house, there will still be some damage entering, water entering the house, so there will always be some damage, right? So in that sense, elevation will reduce risk to buildings more. Next slide, please. So we've also estimated the potential risk reduction because of the storm surge barriers. And the storm surge barriers, because they prevent that the water enters the city, they reduce both the risk to buildings as well as to the economy. And these risk reductions can be very substantial. So for the environmental dynamic strategy, the risk reduction could be about $203 million per year. Well, for the outer harbor barrier, on average, this will be about $232 million per year. And this is larger because that barrier protects a larger area. We've also estimated how uncertain our risk estimates are, because there's uncertainty related to the water level and to the risk estimates. And we know the uncertainty interval between -49 and +63%, so we accounted for that in our estimations. Next slide, please. So now we'll go to the results of the benefit cost analysis that basically combines two pieces of information of the cost and the benefits to see if a strategy is economically profitable or not. Next slide, please. So first of all, for the elevation of existing buildings, we conducted about 36 different benefit cost analyses using different assumptions about discounting, climate change scenarios, different height of elevations. Every calculation showed that it's not cost effective to do that, because all benefit cost ratios are smaller than 1. And the reason is it's just too expensive to elevate these existing buildings. It's not worthwhile the risk reduction that this delivers. So only for some very high risk properties located on the coast, this could be viable, but as a general strategy, it's not viable. Next slide, please. Now for wet floor proofing existing buildings, results are a little bit more favorable. So here I show the benefit cost ratios for two climate change scenarios, so low climate change and high climate change, and different heights to which the building is wet floor proof. And we see here that under the low climate change scenario, and if you apply a discount rate at 4%, so you don't discount the future benefits too much, for 2 feet and 4 feet of wet floor proof in the building, this can be cost effective because the benefit cost ratio is larger than 1. Well, if you have the high climate change scenarios, also increased storminess, it makes sense to do this because under all assumptions, elevation heights, this is actually cost effective because all benefit cost ratios are larger than 1. But it's not cost effective to do this if risk remains constant. And the overall conclusions for the dry floor proofing are rather similar. Next slide, please. We made the sea level rise in 2050, and if there are more severe hurricanes happening, then the city should invest in the barriers. If that doesn't happen, it's not worthwhile to do it. And the net present value, so the profit of the outer harbor strategy is the highest. So that option makes most economic sense, although it may have harmful environmental impacts. And we found that these results are robust according to a variety of assumptions. So we tested out whether the results are the same if you have different lifetimes. So for example, the barriers are not there for 100 years, but if they are there for 150 years. We use different discount rate scenarios, and we also estimated the uncertainty of our risk estimates with a lower bound and a higher bound, and all these conclusions are robust to these model assumptions. The next slide, please. So what are some, general lessons I think that we learned from this study? In general, I think that very destructive events like Hurricane Sandy or the floods that has happened here in Mexico, they always a call for new action, right? So if that happens, people always respond in a way to politicians, we have to do something about this. Right? Also, natural disaster losses have already been increasing around the world, and these are likely to exacerbate in the future due to climate change. So this is also a call for a good adaptation policy. But then again, whether this is desirable to implement or not really depends on the local conditions. So you need to do a local risk analysis like we did for New York. You have to look at how much does it cost locally to implement the measures and then see if it's worthwhile or not. I think economic benefit cost analysis, like we have adopted here, is a good way to prioritize options, right? So the city of New York didn't know whether you need to flood-proof buildings or install storm-surge barriers. Well, with a method like this, you can show what measures is most economically feasible or not. So I think in general, the whole benefit cost analysis methodology with the different models is quite complex. So it took us 4 years to do this. So it requires a chain of models that is affected by large uncertainties. But because here we try to model all uncertainties, so consider a wide range of climate change scenarios, a wide range of discount rates, we accounted for the uncertainty of the model propagation and the risk estimates, then we still were able to arrive at robust conclusions. So I think if there are uncertainties, it doesn't make sense to hide them. You should just try to include them in your model and to see whether your policy recommendations are robust against these assumptions. Why not? Next slide, please. So thank you very much for your attention. So these are some references if you want to learn or read more about our flood risk analysis that we did for New York City. And well, you're all welcome to ask any questions you may have about this research.